The UGC lecture series on computer science. We have the subject theory of computation. As far as the previous episode is concerned, we have studied what is the need for representing the Turing machines in integer codes or in binary form, and then also we have seen that is what is the definition for a diagonal language. Later we have seen that is how a diagonal language is proved as non-recursively enumerable language. So we need to represent the Turing machines as binaries in order to load those Turing machines as input for another Turing machine. And we have seen that as a diagonal language, which is obtained by that is complementing the diagonal of Turing machine with the corresponding that is Turing machine code. And finally we have proved that the Turing machine, there is no Turing machine existing for accepting any diagonal language. So since we find no Turing machine for the language, we claim the language is a non-recursively enumerable language. So as far as this episode is concerned, we are having two different languages. One is called the recursive language and another one is called the universal language, and we have some proofs related with that. So we need to show that is the definition for the that is recursive language, and what will happen for the complement of the recursive language, and what's the meaning of universal language. So how the definition is. Then later we are proving that the universal language is going to be a recursively enumerable language. So these are the things we are having as far as this episode is concerned. So let me start with the definition of recursive language. So it's going to be the there is language L, but the condition here is when there exists a Turing machine for the language, let it be L of that is your M is Turing machine for that. But there are two cases there. One is, so if the string W is in the language of the Turing machine, there is M, which is the L is equal to L of M, then the Turing machine is expected to accept and halt. It means you load any input onto the Turing machine which is constructed for the language L, and if the string is a string accepted by the language or it is there in the language, then you are expected to have the Turing machine halt and accept. That means the Turing machine should come to an end by recognizing the string. Otherwise, suppose if the string W is not there in the language, then the Turing machine has to reject the input and once again halt. So in either way, we are expecting that the Turing machine should come to an end or it should halt, irrespective of whether the string is there in the language or not there in the language. We want to have the Turing machine to halt. So if the language exhibits that property, then we will claim that the language is going to be a recursive language. So this property can be related with the decidable and undecidable problems. Suppose if you find that a Turing machine is always halting, then we can say that there is a problem associated with that, or we can claim the L is associated with the problem and this problem is going to be halting, or the Turing machine which simulates or which performs this problem or solve this problem is always going to halt. In that case, we can expect that there exists an algorithm for that. So we can recall the definition for an algorithm. It's a sequence of steps, finite number of steps, and definitely executed for finite number of times. So there is no question of having infiniteness. So after executing finite number of steps, always we will come to the stop or end if it is going to be an algorithm. So the definition of a Turing machine which is always halting and the definition of algorithm both becomes similar. So that is what, if the Turing machine is expected to halt always irrespective of whether the input is accepted or not, then we can claim that the Turing machine's language is recursive and the corresponding problem is going to be a decidable problem, and if the problem becomes a decidable problem, then we can claim there exists an algorithm for that. Otherwise, so if the language is not expected to that is halt, that is if L is not a recursive language, then the Turing machine is not expected to halt always. Suppose the input W is there in the language, it is expected to halt after accepting, and if the input is not there in the language, then you can't expect that the Turing machine is going to end or going to halt. So in that case, we will call these kind of problems as undecidable problems. So two different types of problems. One is going to be problems where the Turing machines are going to halt always, and there is another one, the problems for which the Turing machines not necessarily to halt. If the Turing machines not necessarily to halt, then we will claim those problems as undecidable problems. Otherwise, the problems are called decidable problems. So now using this concept, we can make use of the recursive language to prove the complement of the recursive language is also going to be a recursive language. So first you should know what is the meaning of the complement of the language. So given L is a recursive language from an alphabet some sigma. So sigma star minus L, that is the entire set of all strings from the alphabet sigma minus L, everything in L. If you get a set of language, then we will call it as L's complement. So what will happen for L's complement given L is going to be a recursive language? You can just recall the definition of recursive language. That is, given a string W, if W is accepted, then it will say accept and halt, and if W is not there in the language, it will say no and halt. So a Turing machine which is simulated or which is constructed for a recursive language is always going to have a halt with two outputs. One is the output called accept and another is the output called reject. So now we have a Turing machine here, that is we call the Turing machine as M. So where we have an input that is W, it may be either in L of M or may not be in L of M. If it is in L of M, we will get accept. If it is not in L of M, we will get reject. So now the question is, what will happen for the complement of the language? We are constructing a new Turing machine, it is called as M dash. So which is going to accept L of M, its complement. So the definition of complement says that a string there in L is not there in L's complement. A string that is not there in L is going to be in L's complement. Which means if a string is accepted by M, then your M complement is expected to reject that. And if a string is not going to be accepted by M, that is if a string is rejected by M, then we want to have M dash accepting the same string. So make it as a Turing machine and you just invert the outputs. So an accept output will be treated as a reject output, a reject output will be treated as an accept output. So now as far as the Turing machine meant for the complement of M is concerned, once again we have two outputs, accept as well as reject. But what this reject is, it is going to be the output of the Turing machine, that is M, in turn it is the output of the Turing machine for M's complement. So as far as M's complement is concerned, if W is there in M, it will say it is reject. If W is there, not there in M, it will say accept. So what we conclude out of this is, we have constructed Turing machine meant for M's complement and which is having two outputs. One is the accept output and another is going to be reject output. So if the problem or the Turing machine is always having both accept and reject output for every string W, either it is there in the there is language of Turing machine or not there in the language of Turing machine, then we can say that the language is going to be a recursive language. So the conclusion is, if the given language L is a recursive language, then immediately we can conclude that L's complement is also going to be a recursive language. So every recursive language whose complement is also going to be a recursive language. So that is the output of this. So next we are having another that is proof similar to in continuation with that. Suppose if L and its complement are recursively enumerable, then we have to conclude that L is also going to be a recursive language. So how we are concluding that is, so you are given two different languages, one is L and another one is called L's complement. The nature of these languages are, the class of language they are belonging to are both recursively enumerable languages. So as far as recursively enumerable languages are concerned, we know that it will accept a string provided it is there in the language of the string, and if it is not there in the language, then it is not expected to halt. It may be looping forever. So no question of having an output for a reject configuration. So a Turing machine constructed for a recursively enumerable language is expected to have only one output, that is only the accept output. If the string is there in the language, we will have accept, the string is not there in the language, no output will be produced. So using this formulation, we can construct Turing machine for L and L's complement. So what do we understand here is, if the W input is given as input for both L and L's complement, that means M1 meant for L and M2 meant for L's complement, then an accept output from M1 is telling that W is accepted by this M1, and an accept output from M2 is telling you that W is not accepted by the language, W is not there in the language L, or it is saying that W is there in L's complement. So we have two outputs, both are treated as accept outputs, but from two different Turing machines, both are constructed for complementary languages. One is for L and another one is for L's complement. So what we will be able to conclude out of this is, this accept says that W is a string there in L, and this accept says that W is a string not there in L, or it is saying that W is a string which is there in the complement of L. So if it is there in complement of L, it means that it is certainly not in L. So now we extend the output of both. So this will be the accept output of the first Turing machine, which is M1 meant for L. You just direct it as the output, or you just draw it as the output called accept, and you take this accept as the output, extend it and treat it as reject. Now let us see the whole that is Turing machine formulation. We have once again a problem which is a Turing machine M, which is constructed out of two Turing machines M1 and M2. We know that M1 is constructed for L and M2 is constructed for L's complement, and the new Turing machine is having both accept and reject output. So what we understand from here is, if L is a language which is recursively enumerable and L complement is the complement of the L which is also recursively enumerable, we can conclude that is M is going to be a Turing machine which is having both outputs, that is both means the accept as well as reject. If you are having both outputs, immediately conclude that L is going to be a recursive language, in turn L's complement is also going to be a recursive language. So if L is recursively enumerable and L's complement is also recursively enumerable, it implies that both L and L's complement are going to be only recursive languages, because of we find that if W is there, then we are getting accept, if W is not there, we are getting the reject output for the Turing machine called M. So this is what another proof we are having as far as the recursive languages are concerned. So then we have a different language called universal language. So in the previous episode, we have seen a language called diagonal language, which is formed out of the characteristic vector which is obtained from the diagonal of the table which we have formed for the intersection of Wi and Mi, where I is the ith string in the lexicographic ordering obtained for the there is set of all strings from the alphabet called sigma, that is nothing but 0, 1. And here we have a language called universal language. So first of all, you should know that is what kind of strings are going to be there in the language universal language. The set of all strings which are there in diagonal language are, so Wi is such that Wi is not going to be accepted by Mi, where the pattern Wi and Mi are ith string in the lexicographic ordering from the alphabet sigma is equal to 0, 1. That means both are going to be same. But whereas in the case of universal language, here we find that the pairs, that is M, W, we will include the strings, that is M, W, into the language called LU, but the condition here is, it is not required that M and W must be same, but the condition M should accept W. So if you take a pair, that is a Turing machine and an input, that is W, if W is accepted by M, then the pair, that is it is not M exclusively or it is not W exclusively, but the pair M, W will be there in the language called, in the set, and that set of strings will be called universal language. And we have to show that the Turing machine for U that is for LU is always existing, and we call the Turing machine as universal Turing machine. So universal Turing machine means we call the language as LU, and the language of the Turing machine, that is L of U, will be called LU, which is nothing but universal Turing machine. So now it is required to prove whether this language is going to be a recursive language or it is going to be a recursively enumerable language. After a break, we shall see whether the universal language is recursively enumerable or not. Welcome back. We are seeing the definition of an universal language. It is a set of all strings formed by the pair m comma w, where m is a Turing machine and w is the input for the Turing machine, and we can say that this string, that is m comma w, will be there in the universal language only if m is accepting the string called w. So now we need to prove that the language, that is LU, which is the universal language, is called a recursively enumerable language. First we should understand what should be proved to claim that the language is going to be a universal language. So if there exists a Turing machine for a language, then immediately we can claim that the language is going to be a recursively enumerable language. In the previous case, we proved that there exists no Turing machine for the language LD, that is diagonal language. That is why it was declared as a non-recursively enumerable language. But as far as this case is concerned, we are going to prove the language as recursively enumerable. It means we should prove that there exists a Turing machine for the language, which will tell you that the language is going to be a recursively enumerable language. And later, we have to prove that the language is not recursive. It is not required that every recursively enumerable language must be a recursive language. The difference there is, if the language is a recursively enumerable language, only the strings there in the language will be accepted and the Turing machine is expected to halt, but no output about the rejection. But at the same time, if the language is going to be a recursive language, it is expected to have both outputs, that is accept as well as reject. Here we are going to prove this language, that is your universal language, as recursively enumerable. It means there exists a Turing machine for that, which will produce the accept output only if the strings are accepted by those Turing machines. So let's see how the Turing machine is constructed. So first we will go for constructing the Turing machine with a multi-tape, and then we will be having some number of tapes. So the input string, first of all, that is m comma w. Here we should understand what this m is. M is the Turing machine and w is a string accepted by the Turing machine, and this pair is the input for a Turing machine which is called as u. So we load the input, that is m comma w, into the first tape of the Turing machine meant for u. We know this is going to be an universal Turing machine which is implemented with the help of multi-tape. So in the first tape of the Turing machine, m comma w, you just load that is m comma w as the input. Then the second tape is used for simulating the behavior of m, because m itself is a Turing machine. It will be having some number of transitions, and it is available in the form of integer code or binary string. We will be having c1, c2, etc. up to some cm followed by this w. So you have to read, there is every transition from this m, which is available in the form c1 followed by 2 consecutive ones followed by c2, etc. And that will tell you that is how this Turing machine is behaving, or how we are simulating the behavior of the Turing machine m. See what will happen here is, first we need to verify whether the Turing machine is going to be a valid Turing machine or not. To see whether this Turing machine m is a valid Turing machine or not, you just check it out that whether c1 followed by 2 consecutive ones, then followed by c2, etc., etc. up to cn are all there or not. And for each ci, so there is a format available, because there are 5 values are there, 2 inputs and 3 outputs. So the string must be of the form 0 power I, 1, 0 power j, 1, 0 power k, 1, 0 power l, 1, 0 power m. So if you are able to find out consecutive, that is codes of this format, then we can say the Turing machine code is a valid Turing machine. And suppose if the Turing machine code itself is not a valid Turing machine, then we can immediately claim that the language of the Turing machine is empty. So now we will go for initializing the second tape with w in binary coded form. that is in the second tape of the Turing machine. So now what should be done? So start state, there will be start state available for this M, which is the Turing machine loaded as the input, and that is loaded into the third tape of the Turing machine. The start state is going to be maybe it is Q1. Since it is going to be the very first state available in the list of states, we will represent it in the unary form with the help of 1 0 on the tape. So now we have the start state, and then we have to find out the input, that is which is already available in binary coded form. So both the inputs, that is the inputs required for the simulation of M, are now available both in the second tape as well as in the third tape. So once you know the inputs are already available for us, we have to find out the output for the input. Suppose if we find that 1 0 is there in the third tape, which is nothing but the first state, and 2 zeros in the second tape, which is nothing but the second symbol from the tape alphabet of M, maybe it is 1 or 2 anything. Now knowing these two, we can form a prefix 0 power that is 1, a 1 followed by 0 power 2. It means the very first state and the second symbol as the current symbol, we have a prefix 0 power 1, 1 followed by 0 power 2. Then we are looking for a code from the Turing machine, that is M, which is in the first tape of the Turing machine called, that is your universal Turing machine. See whether there is a match available or not. And once we find a match for 0 power 1, 1, 0 power 2, then we can read the remaining 3, that is symbols, or remaining 3 components, which are nothing but the output of the current transition. The transition is what is going to happen for del of Q1 comma the symbol which is 1. So if the output here is, for example in this case, here we find that I is the current state and J is the current symbol in the tape. Now if you find there is a code whose prefix is 0 power I, 1, 0 power J and then 1, what is going to be the remaining components of that string? So it is of the form 0 power K, 1, 0 power L, 1 and then 0 power M. It is going to be there in the tape 1 of the Turing machine called U. So this could be interpreted as del of Qi comma, that is jth symbol, is going to be, the output is Qk comma lth symbol, maybe some XL comma the direction to move is the mth direction. So now we need to execute this output. What it means is, go to the third tape, replace this 0 power I by 0 power K, since it is going to be resulting state, and then go to the second tape, replace this 0 power J by 0 power L, and we would resume this processing by executing the direction called M. So this M is going to direction, it can be the mth direction. So as far as the current tape content is concerned, that is nothing but the tape 2, there is a need for moving towards left or right based on the direction M. So that is what the simulation behavior. So we have the explanation here, replace 0 power I in tape 3 by 0 power K, and thus the current state is updated. Then replace 0 power J in tape 2 by 0 power L, and thus the tape content is that is also updated as far as the Turing machine M is concerned. And then what should be done is, locate the next tape symbol by depending on the M, that is the direction in which we have to move in the tape called, that is 1. So after doing all these things, we can claim that one step or one transition has been executed. Since it is going to be a multi-tape Turing machine, so all these can be independently done, so without any difficulty, and keep doing this process as long as we find valid input and outputs with this kind of information, that is both input and output, we have the codes. So suppose we find that there is no question of having a transition like that, so in that case your Turing machine is going to halt. So if you find that there is no valid move, then M halt, and it means U is also going to halt. If M is accepting or M is going to enter into an accepting state, then immediately we can claim that it is U is halting, that is the Turing machine is going to halt by accept. So two cases, M may accept because of that you will declare that u is going to accept, and if it is going to be an accept, then we can claim that it is going to be a halt operation. So if it is going to be the case, then we can say that the universal Turing machine u is also going to accept the pair m comma w, which is nothing but an input for your Turing machine, provided if and only if m is going to accept w. So this is sufficient to show that the Turing machine, which is nothing but meant for your LU or the universal Turing machine, is going to be existing, and the language is called recursively enumerable language. So now how do you prove that the language LU is not a recursive language? So here we have a contradiction proof by contradiction. Suppose if LU is recursively enumerable, and actually that is what given, LU is recursively enumerable, but we need to show that LU is not a recursive language. If LU is recursive, by the proof that every recursive language complement is also recursive, we will find that LU's complement is also a recursive language. If LU is recursive, then LU's complement is also recursive. So then it means that we will be having a Turing machine for LU's complement. LU is recursive, which means LU's complement is also recursive. If it is going to be a complement whose language is recursive, then we can claim that there exists Turing machine for LU's complement. We know that the complement of the LU is going to be have some similarity with your LD. It means if we can find a Turing machine for LU's complement, it is possible to construct a Turing machine for LD, which is going to be a contradiction, because we have already proved that the language LD is a non-recursively enumerable language. But here if you are able to construct a Turing machine for LD, which is contradicting the proof that LD is a non-recursively enumerable language. If we assume the LU is recursive, then we will be able to have a hypothetical Turing machine like this. So we will be constructing a Turing machine M for the language called that is going to be LU, and we will be giving the input W, but using an algorithm for copy, we will convert W into W followed by 3 consecutive ones followed by W. So it is of the form a Turing machine M comma W. So that is what we need to have as far as the input for the Turing machine that is LU is concerned. This completely assumed as hypothetical Turing machine. So if it is given as input, then by the assumption that LU is recursive, it will produce accept and reject output, and you just take the inverse of this, because LD is going to be the complement of this particular language, because here it is saying that W is there in M, or if M is accepted W, we will say accept, but as far as LD is concerned, if M does not accept W, then we can say that it is going to be a reject operation. So you just complement the outputs, accept as reject and reject as output, then we can say that there exists a Turing machine for LD, which is completely contradiction, which gives us the proof that LU is going to be a recursively enumerable language alone, but not going to be a recursive language. So what we have seen so far, it is the recursive language, definition of the recursive language, and then we are having the there is a proof, which is nothing but the complement of a recursive language is going to be a recursive language. Then afterwards we have proved that suppose if L and L complement both are recursively enumerable languages, then it's called, that is, both L and L are recursive languages also. Then later we have seen the definition for universal language. So the universal language is the one which will be having a set of all strings of the form M comma W, such that M accepts W always. So M comma W will be there in LU, and a string of the form M comma W, if M does not accept W, it is not going to be there in the language called LU. And we have proved that the LU is going to be a recursively enumerable language by constructing a Turing machine for, that is, LU, and later we have seen that the Turing machine for LU is existing, but the LU is still not going to be a recursive language. So if LU is assumed as a recursive language, then we can show that the LD is also going to be a language for which we have Turing machine. So we proved that the universal language is recursively enumerable but not recursive. So the, as far as the question components are concerned, so we need to prove that the complement of a recursive language is also a recursive language, by constructing the formulation for Turing machines. And what is the meaning of universal language? So what is going to be definition for that? And proving that the universal language is recursively enumerable but not a recursive language. So related the questions are possible in terms of this one. In addition with that, we have seen there is two kind of problems. One is called the desirable problem and another one is called the undesirable problem. So if the language is recursive, then we will be calling those kind of problems as desirable problems. If the language is a not recursive language, then the problem is called an undesirable problem. So those things we have seen as far as this particular episode is concerned. With this, I conclude this episode. Thank you.